backwards. Perfect. All right. Hello, everyone. My name is Nick Paddock. Today, I'll be presenting my work on Project 45, High-Yield ETH-Exposed Strategies in Decentralized Finance with our project sponsor, BTCS. This is one of our younger projects here. We just started work on it in September just to get a little more in line with BTCS's current business with their new decentralized finance branch. And so we're essentially looking to find alternative ways to get yield on their large holdings of Ethereum. And with the README we were given, we decided to settle on doing strategies with liquidity provisioning. The active liquidity provisioning is essentially we are going to take some amount of capital. We are going to deposit in a liquidity pool. In this specific scenario, we're depositing our capital into Uniswap. Uniswap is a decentralized exchange where users can go in and swap specific tokens across the liquidity pools. And we're choosing to deposit our assets and provide liquidity to these liquidity pools to enable these transactions to occur without large price slippage and just overall as easy as possible for the users. The way that we actually receive money from depositing this liquidity is by fees. These fees are directly paid out in proportion to the fee tier. Every single one of these liquidity pools has a fee tier on the right. Any amount of volume that moves through it, percentage of that is then turned into fees, which is then in turn paid out to liquidity users based on their amount of active liquidity, which I'll be touching upon shortly. But a little bit more about Uniswap. We're specifically focused on version 3 of Uniswap, which allows for concentrated liquidity. What that's saying is Uniswap v2, if I go to deposit my liquidity in a Uniswap v2 pool, I'm depositing my liquidity across the entire range of the price from negative infinity to infinity, and so is every other user. What Uniswap v3 allows for is for me to choose a concentrated price range. So I can say, this is directly from their website that I pulled yesterday, I can take the current price of Ethereum to USDC, and I can deposit from the current price within a specific band. This example, I'm depositing from a price range 30% above the current price of Ethereum to 30% below the current price of Ethereum. And since my liquidity is now more concentrated, I'm able to be more capital efficient and earn more fees for a smaller amount of capital that I'm allocating to this liquidity pool. So overall, the Uniswap v3 allows for more mathematics to happen behind the scenes and more capital efficiency, which is what we're looking for, since it allows us to derive higher yield on a smaller amount of investment. So in terms of actually calculating our overall risk and return here, we use this return calculation, which is just the fee profit, which I mentioned is derived from all of the volume that's moving through. We're receiving some fee profit based on that. And then we have the actual change in value of our position. Say I invest $100,000 in capital into this. It is still being subject to price movement in Ethereum if I'm investing on that USDC Ethereum pool that I mentioned. So say I have $100,000 and that's moving as it goes. That change in the value of the position is all accounted for here in the return. And then we have our impermanent loss. Impermanent loss is essentially saying what is the value of that original $100,000 investment at the final price. So say I invest $100,000, it will not end the actual value at the end. The actual value at the end of that $100,000 is $88,000. If I had just strictly invested that $100,000 outside of the liquidity pool, it would be worth some different amount than that. That price difference is our impermanent loss. And then overall, we have the gas fees that occur. Whenever I mint a position or create a position, and whenever I burn a position or destroy my position, I have to pay some amount of gas fees, which is likely less than $100. And given the returns that we get, it's not accounted for here, but they're small enough that the overall percent error that brings is not relevant to us. Of course, for impermanent loss as well, something to account for is the higher our price range is, the less impermanent loss we face. So if we take a riskier position that's more likely to fall inactive because the price moves, then we are going to be facing more impermanent loss throughout that process. So in terms of some actual a database called The Graph, they have a large amount of blockchain data, specifically for Uniswap. So I pulled in all of our active liquidity data. So basically, how much liquidity is active at that time. Say I deposit $100,000. How much will I be being paid out based on that amount of active liquidity? How much percentage of that active fee will I be garnering? And then, of course, I pulled the fee amount that's paid out every single block. And then as well as that, you need the current price to tell if my position that I'm depositing over is active or inactive, because if the price falls out of the price range that I've deposited over, I'm no longer earning fees. So I pulled this for the aforementioned Uniswap v3 USDC Ethereum pool. It has a 0.3% fee tier. As I mentioned, fee tier I'm going to be getting 0.3% of the fees and then whatever percent of the active liquidity I have. And I have hourly price data for this. And then it's for the entire length of the contract up until when I started the project. The contract began on May 4th, so that's when I pulled data from. So not the longest span of time, but enough that we were able to get an initial backtest on it. And in terms of our actual backtest, a fully configurable backtest written entirely in Rust, just for the speed. So I can go in, I can say, I want to start at this date. I want to have this set price range for my liquidity provisioning. I want to have this strategy type, which I'll be going into, the 3 strategies that I derive for this. What amount of deposit do I want in dollars? And then it'll automatically translate that into the amount of active liquidity we have. And then overall, we have the returns calculation, as I mentioned, and then we plot all our results outside of the backtest, just strictly using Python. So in terms of actually execution for the simulation, from this point forward, we're going to assume that the constant deposit and a constant alpha. All alpha is how we derive our price range. So if I have a 1.3 alpha, I'm depositing my liquidity 30% above and 30% below the current price range. And for when I say a constant deposit, if I am depositing multiple times over our simulation window, say I deposit $1.5 million, at the end of the first deposit, it's now worth $1.3 million. I'll deposit another $200,000 to get back up to that initial $1.5 million deposit. On the right here is a picture of a static strategy. We say for the 120 days that the simulation occurs for, we have our position labeled in green there. So whenever we're earning fees and we're active, the price is within our position and it's listed in blue. And then whenever we fall inactive, it's outside of that green hue and it falls orange and we're not earning fees at that time. So we're looking to optimize for how can we earn the most fees, how can we keep our price range tight enough that we can be the most capitally efficient, but also not fall out of becoming active. So we look at some previously published work here. This is the second strategy I mentioned. They established a tau reset strategy. This is about as bare bones of a dynamic strategy you can get. When I say dynamic, all I mean is that I'm going to be rebalancing multiple times throughout my window rather than just strictly saying over the whatever backtest I'm holding one position the whole time. So we have a dynamic strategy here where we say the moment our pool falls inactive, we're going to burn the old position and immediately mint a new one based on that constant price range and that constant deposit size. This, like I said, bare bones, the only thing you can optimize for physically is what price range you're depositing over, what is your deposit size. And since we're assuming that's constant, there's really no optimization for us to do at this point. So we use this as our baseline model for dynamic comparisons. And then in terms of some overall results here, this is for a 1-year simulation starting, I believe it's about May, but we actually are using our time in blocks in May 2022, sorry. So our time is actually in blocks. A block is every 12 seconds. So when I say hourly data, I'm saying I have data every 300 blocks. So we simulate over, I believe this is about 250,000 blocks that we're simulating over a full year. And we have a total initial investment of $1.5 million. But then as that price is moving and we need to rebalance up to $1.5 million, our overall total investment becomes $3.62 million. But our overall fee profit at the end we make is $2.68 million in addition to that investment that we get back at the end. So we get an overall APY of 73.37%, while Ethereum performs at negative 32%. So as I mentioned earlier, the overall strategy that we're looking for is how can we avoid against situations like this where we are getting gains on our Ethereum that we're holding outside of just strictly holding it. So this is where I introduce my strategy that I've come up with here. So we have the vol reset strategy, as I've named it, because it's based on volatility. So the previous work, as I said, you can optimize for the what. There's no optimization for the when. You fall inactive, you immediately balance. The idea here is that we are going to optimize for the when. How can we introduce when we want to burn the position, when we want to mint a new position? So I come up with these ideas of 3 main sources on determining when we burn, and then 1 main source on determining when we mint. So the project focus is how can we optimize for how close we're falling to inactive, what is our current volatility, and how long are we inactive to figure out when we burn, and then what is the current volatility for when we mint. So overall, I do some hyperparameter tuning. Essentially, I'm going to take 100 different values of price threshold and volatility threshold and run the simulation for all different combinations of those 100 parameter or 100 values. I'm going to burn the position if we already have an open position. If our current forecasted volatility is above the volatility threshold, then I'm hyperparameter tuning. And then if our contract price is within price threshold percent of either bound, so if I have a price threshold of 1.03%, say I fall 3% below becoming active, that's when I'll burn the old position. And then I mint a new position if I currently don't have an open position and volatility is low enough that it's time for me to rebalance. So in terms of forecasting realized volatility, I'm just using a heterogeneous autoregression model. It's essentially, I'm just doing a linear regression focused on realized variance because that's not essentially the focus of the project. In the wise words of my boss, if this was a project about calculating volatility, we would make more money doing that. So we use a pretty baseline model here. And this is our overall results. We get the 1.5 initial deposit. We end up depositing total $3.31 million that we make back at the end. But throughout that $3.31 million deposit over a year, we make a total fee profit of $2.94 million. This is over the same simulation window as I had for the previous strategy. So we have the same Ethereum loss. However, if we compare it with the other strategy, we have a smaller overall investment and still greater overall fee profit. And that's because we are staying inactive in the orange during periods of high volatility, which is exactly what we're trying to achieve, is how can we stay inactive during these high volatile periods so we don't fall inactive and face the large and permanent loss or large value loss on our position. So actually comparing all of our strategies on top of each other here, in green, we have the vol reset strategy that I mentioned. Performs well sometimes, doesn't beat the other strategy sometimes. It's something we're actively working on. Like I said, this is a young project. We're going to be handing it off shortly since I'm graduating. But then overall, the idea is that we do outperform the Ethereum performance, which is what we were looking to do to begin with. But as I said, we do have some downfalls here, and it's that we are using hourly price data. ETH is a very volatile asset, and we do have periods where we can fall $400, and that's a 1 hour span. So we do stay active during a long drop here that if we had minute data per block data every 12 seconds, we would be able to avoid this scenario, and that's exactly what a bit of the future work is focused on, is how can we then further optimize for the things I mentioned we weren't optimizing for. How do we optimize the deposit range or the deposit size? How do we optimize the price range? How do we then incorporate different pools? Like I said, we're just working on one singular pool, but there's thousands of pools on Uniswap. They don't have to be meme coin based. They can be something that I could deposit my money into a stablecoin pool, which I'm expecting to trade at $1 because they're both priced at $1. So when I'm swapping between them, they're going to be pretty constant, and I'm going to stay active as long as possible. So these are all things that we've heavily considered that will be for the people we're passing it on to. But as an overall summary here, what we look to do is just create a back tester that can perform liquidity provisioning strategies, which we achieved. And then, like we set out to do, we outperformed long ETH with a volatile aware strategy, and we outperformed our baseline strategy fairly well as well through the volatile aware strategy. And yeah, that's what I got.